Welcome to this lesson about systems. I will speak about elementary systems or off-the-shelf systems because they are commonly used in many applications. Keep in mind this little mathematics. So remember that the convolution in the time domain is equivalent to the product in the frequency domain and vice versa, and that a system, a linear time-invariant system, can be completely defined by this impulse response, h of t, or this transfer function, h of f. So let's see the first very simple system, which is the amplifier. So the amplifier is a system that multiplies the input by some number, a, so that the amplitude of the output is different from the amplitude of the input. The transfer function of the amplifier is a constant, the constant a, at least in the bandwidth where we are interested, so for the bandwidth of the input signal. And we have here an example. So the signal in blue is the input, the signal in red is the output. It has been multiplied by 3. It can be think like a volume in a stereo amplifier. Other systems perform some frequency filtering, so they can reduce, they can increase, they can reject some portions of the frequency component of the signal. So usually the frequency components that are retained, they are called pass. The frequency components which are not retained, they are called no pass. And there is a transition between the pass zone and the no pass zone. If the frequency components that are in the pass region comprehend the zero frequency, this is called a low pass filter. So low pass filter is a filter that takes all the frequencies from 0 to an upper frequency that I can call cut frequency. A bandpass filter instead is a filter that can retain all the frequencies between the frequencies f1 and f2. And high-pass filter is a filter that can retain all the frequencies above some cutoff frequency. So these three panels are the transfer function of the low-pass filter, the bandpass filter, and the high-pass filter. I have an example of this filtering applied to a music. Depending on the position of the pass frequencies or the no-pass frequencies, you are enhancing or reducing the contribution of some instrument. So this is the vision of a graphic equalizer. So you can, by moving these sliders, you can increase or decrease the frequency component of each one of these frequency bands. So the example is here. This is the original sound. When I click here, you hear the original music, so without any filtering. Now I am applying a filter which is enhancing the low frequencies and reducing the high frequencies. So it will sound more low frequency in the sense that we are losing the violins, we are losing the high frequency components. Let's hear it. And finally, I am enhancing now the high frequency components. So you are losing the drums, you are losing the low frequency instruments. Let's click it. Okay, you could hear the difference. So the graphic equalizer is a way to increase or decrease a particular range of frequencies and so obtain different sounds in output to the filter. We have next the delayer. It's a very simple system. The output is a delayed version of the input. You can use this system to produce reverberations, echoes, and change you produce on the signal is just a change in the phase. You see that the amplitude spectrum is unitary, so you are not doing nothing on the amplitude spectrum. You are just contributing a different initial phase to every sinusoid of the signal so that the net effect is a delay. Here is a very simple example. So I am delaying the input by 5 seconds. So the red line is delayed by 5 seconds with respect to the blue line. Now it comes another kind of off-the-shelf system, which is called modulator. What happens if you multiply a signal x of t by a cosinus? So remember that multiplication in the time domain is convolution in the frequency domain. So when you do the Fourier transform of x of t, you get x of f. When you do the Fourier transform of the cosinus, you get two impulses. And when you do the product here, is the convolution here, that means that you are moving the spectrum of x of f centered in the position of minus f0 and plus f0, where f0 is the frequency of the cosinus. So this is a way of shifting the spectrum of a signal around a frequency which is called the carrier frequency. What is the application of this kind of filter? You can start with some kind of signal which has a spectrum in some region of the frequency axis, and you can move this spectrum up and down to the frequency axis depending on the transmission you want to perform with this kind of signal. Let's see an example. So suppose you have an acoustic signal that is in the bandwidth between 20 and 20,000 Hertz. So this is an acoustic vibration which is recorded by the microphone and converted to an electrical signal. The electrical signal is a copy of the acoustic signal, is still in the bandwidth 20 kHz. You want to convert this signal to an electromagnetic wave because you want to do some radio broadcasting, and the radio broadcasting is not effective. It doesn't perform very well in this frequency, so you have to move the spectrum of the signal in an upper frequency, and this is the function of the modulator. So F0 is in the range of some kilohertz up to megahertz, depending on the bandwidth of the radio that you want to use. So you move this signal, which is originally in the bandwidth 20,000 at an upper frequency. You transmit in an efficient way the electromagnetic wave connected to this signal. And then there is also the possibility to do the demodulation. The demodulation is still done by multiplication of a cosinus, and you can bring down the spectrum of the system to the original spectrum, 20 kHz. And then you can feed the speaker, and you can hear the original signal. So this sequence of operations are casting the signal to the best and more efficient bandwidth depending on the system you are considering. So if you want to do a radio transmission, you have a certain range of frequencies. If you are in the electrical field, another range. If you are in the acoustic field, this is the range of frequency that we are able to produce with our voice or with our music. And this ends the lesson about elementary systems.